In this lesson, we're going to learn about stoichiometry, which is the relationship between the mass and mole of substances in a chemical reaction. So for example, if I start with a certain amount of a reactant, how much product will be yielded in that reaction? So for this, I need a balanced chemical equation, because a balanced chemical equation tells me the mole-to-mole ratio of substances needed and substances that will be produced. However, that does not tell me in terms of a mass, which is what I would actually measure for how much reactant is needed and how much product can be expected. So the relationship between the mass of a substance and its number of moles is connected by its molar mass. So every single substance has a different mass per mole because it's made of different types of atoms and different numbers of atoms. So the molar mass here is going to be key to the connection between the mass and mole of a substance, and it's the mole-to-mole ratio of one reactant to another or a reactant to a product that is important here. So if you want to, there is a PhET simulation in OneNote in the content library that you can carry this mini investigation out with, and these instructions are also in that OneNote page. So for example, in the Haber process, ammonia and hydrogen react to produce ammonia gas. In the ratio they react in is 1 mole of nitrogen for every 3 moles of hydrogen, and that ratio will yield 2 moles of ammonia. So up until recently, we've talked about this in a number of molecules. So 1 molecule of nitrogen will react with 3 molecules of hydrogen to produce 2 molecules of ammonia. But atoms are incredibly tiny, and so in order for us to see them, there are going to be many, many molecules of an element or a compound. So we've recently talked about Avogadro's constant, which is 6.02 times 10 to the 23 of something. And so we are going to start referring to the coefficients not as molecules of an element or compound, but as the number of moles of an element or compound, which will yield an amount that we can actually see and measure. So we're going to take a look first at the mole-to-mole relationships, and then after that we will look at tying in the mass, which is what we can actually measure. So how many moles of hydrogen gas are needed per mole of nitrogen? So I'll start with from the balanced equation. So hydrogen gas, I have 3 moles of hydrogen for every 1 mole of nitrogen, and I'm asked per mole of nitrogen. So I'm already in per mole. So how many hydrogen? So I need 3 moles of hydrogen for every 1 mole of nitrogen. How many moles of ammonia are produced per mole of nitrogen? So I have 2 ammonia per 1 nitrogen in my balanced equation, and I'm asked per mole. So I already have 1 mole of nitrogen. So for every mole of nitrogen, 2 moles of ammonia are produced. So these are nice and simple because I'm being asked per mole of nitrogen, and I have 1 mole of nitrogen in my balanced equation. So what happens when we have different ratios? So how many moles of ammonia? So in my balanced equation, I have 2 moles of ammonia for every 3 moles of hydrogen gas. But I want to know how much ammonia is produced for every 1 mole of hydrogen gas. So this is for 3 moles, which means I can divide this by 3 to get to 1. I would do the same to ammonia. So 2 divided by 3, 0.67. So 0.67 moles of ammonia would be produced for every 1 mole of hydrogen gas. And this, being able to do this is going to be key for our conversion for a mole-to-mole ratio between 2 substances, and then on either end we will be connecting the number of moles with the mass. So our next example, rocket fuel. So Apollo landers used hydrazine, so that's N2H4 fuel. So 2 hydrazine will react with 1 dinitrogen monoxide to produce 3 nitrogen and 4 water. So how many moles of hydrazine? So hydrazine is 2 moles do you need per mole of dinitrogen tetroxide? And in the balanced equation, I have 1 mole of dinitrogen tetroxide. So I need 2 moles of hydrazine per mole of dinitrogen tetroxide. How many moles of nitrogen per mole of hydrazine? So nitrogen, I have 3 moles produced for every 2 moles of hydrazine that are reacted. So how much per 1 mole of hydrazine? So I need to divide this by 2, divide that by 2 as well. So 1.5 moles of nitrogen are produced for every mole of hydrazine. Example 3, aluminum metal reacts with chlorine gas. So the first thing we're going to do is write a balanced chemical equation. So aluminum metal are metals we find as single atoms when we write our balanced equations. Aluminum is a metal, so it's a solid. Reacts with chlorine gas. So we know from Hofbrinkel or from the 7 valence electrons that when 2 chlorines come together, so they'll share 1 electron each, both will then have 8 in its outer shell and be stable. So I need 2 chlorine, and it tells me already that that is a gas. That's also in your periodic table. The electronegativity one gives you for elements what their state is. So when those react, I have a metal and a nonmetal, so that's going to make an ionic compound. And for those, I can figure out the chemical equation using valences, so what ratio they will combine in. So I need 1 aluminum for every 3 chlorine. And ionic compounds have very strong intermolecular forces, and so those are going to be solid at room temperature unless they are dissolved in water, in which case they would be aqueous. So here I have 1 aluminum, 2 chlorine, 3 chlorine. So on the reactant side, chlorine comes in groups of 2. On the product side, it comes in groups of 3. So if I have 6 total chlorine atoms, that works for groups of 2 and groups of 3. So I would need 3 groups of 2 to get to the 6 and 2 groups of 3. So I have 6 chlorine atoms on each side, reactants and products. I also now have 2 aluminum, so I need 2 aluminum over here. And now the equation is balanced. So the next thing I'm going to do is, based on that balanced equation, I'm going to calculate the number of moles I would need of the blank reactants and products there based on the piece of information I have. So from my balanced equation, 2 moles of aluminum react with 3 moles of chlorine to produce 2 moles of aluminum chloride. So if I have 2 moles of aluminum, that is what is in my balanced equation, which means as I fill these out, I'm just going to have the exact same as my balanced equation. So 3 moles of chlorine, 2 moles of aluminum chloride. So from here to here, what is happening is I have a division of 2. So I have half the amount of chlorine that I have in my balanced equation, which means I would also need half of the amount of aluminum, and I would produce half the amount of aluminum chloride. So we can take a look at the relationship from our balanced equation to how much we have of the chlorine. The other direction we could look at it is in our balanced equation, what can we use? So our relationship is however many aluminum atoms I have, that is the same number of moles of aluminum chloride that is produced. And then the relationship between aluminum and aluminum chloride and chlorine is, to go from here to here, I would need to divide by 2 and multiply by 3. And in this direction, I would need to divide by 3 to get to 1 mole of chlorine and then double that. So we can also see this as, so multiplied by 3 divided by 2 is the same as multiplying by 1.5, and multiplying by 2 dividing by 3, that's also the same as times 2/3. So there's kind of multiple ways that we can see this. So number of moles of aluminum chloride, so that's the exact same as my number of moles of aluminum, so I can fill this in here. And then moving from aluminum to chlorine, I divide by 2, so 0.8 divided by 2 is 0.4, and then multiply by 3. 0.4 times 3 is equal to 1.2. Next one, I have 2.4 moles of chlorine, so how much aluminum and aluminum chloride would I need? So from here, I'm going to divide by 3 and then multiply by 2. So 2.4 divided by 3 is 0.8. 0.8 times 2, 1.6. And aluminum chloride are the exact same. So next one as well, aluminum and aluminum chloride are exactly the same. So 0.3 moles of aluminum chloride. And to move to number of chlorine, so my relationship tells me divide by 2 and multiply by 3. So 0.3 divided by 2 is 0.15, times 3 is 0.45. So if I had 0.3 moles of aluminum, I would need 0.45 moles of chlorine to react with it, and that would yield 0.3 moles of aluminum chloride. So our balanced equation, which we started learning how to do in grade 10, gives us the lowest terms whole number ratio of how many moles of each element or compound I need and how many to react with one another, and then how many moles of each element or compound in the products will be produced. And that is going to be needed to determine the masses of those substances. So the issue with just number of moles is we don't have a device that measures moles, because the number of moles for each substance is going to be different in terms of mass, because every substance is made of different types of elements and a different number of each of the atoms it's made of. So what we will measure is a mass, and we can use the molar mass to make that connection between the mass and the number of moles of a substance. So we need to make that conversion. So if we start with the mass of a reactant, we can convert that to a number of moles of that reactant by taking the mass and dividing by its molar mass. We can then do what we just did, is use our mole to mole relationship, so the coefficients in the balanced chemical equation, to get to the moles of the product, and then we can convert the moles using the molar mass into the mass of the products. Now this mass to mass stoich, you can do that from mass of reactants to mass of products, but you can also use it for the mass of reactant 1 and converting to what mass of reactant 2 you would need for that. So this is really just a mass to mass conversion of any substance in your balanced equation to another substance. So it can be reactant to other reactant, reactant to product, one product to another product. So it's really just going from the mass of one substance to the mass of another using the mole to mole relationship in the balanced equation. So what does that look like? So if we go back to the Haber process, so nitrogen and hydrogen reacting to make ammonia, how many grams of hydrogen are needed for 18.6 grams of nitrogen? So I'm going to start with my mass of nitrogen, convert that to how many moles of nitrogen there are, then use my balanced equation for the mole to mole ratio, and then convert that number of moles of hydrogen into a mass of hydrogen. So I am going to use the unit canceling method here. At the end, I will go through this question using the formulas and the mole to mole ratios and doing it as separate steps. But this is a more efficient process. It helps us with not having answers at the end of 3 calculations and having to round at each time. And hopefully also helps understand putting each of the values in the correct place based on those canceling units. So if this makes sense to you, you can use this. If not, at the end, I'll go through the other method and you can use that for the questions. So to start with, I have 18.6 grams of nitrogen. Now I want to convert that into a number of moles of nitrogen. And for that, my connection between my mass and my moles of nitrogen is the molar mass. So my molar mass of nitrogen, each nitrogen has 2 atoms of nitrogen, which has an atomic mass of 14.01. So 28.02 grams per mole is the molar mass of nitrogen. So the way that I'm going to put that in here, so each of these lines signifies a multiplication between a fraction. And so over here, I want my mass of nitrogen on the bottom so that those units will cancel. So my molar mass for nitrogen is 28.02 grams of nitrogen for every 1 mole of nitrogen. So here you're going to have the same element or compound. So this whole thing is the molar mass. And in the equation, we take the mass and divide by the molar mass. So that's why I have moles per gram instead of grams per mole for how this is set up. So my grams of nitrogen will cancel this way. That would convert to how many moles of nitrogen I have. So this is per 1 mole always, because my units for molar mass are how many grams per 1 mole. So I don't write the 1 here, but as I put this over here, my molar mass relationship is always going to be a per 1 mole. So the next thing that I would do is use my balanced equation to convert from a number of moles of nitrogen to a number of moles of hydrogen. So for every 1 mole of nitrogen, I need 3 moles of hydrogen. So that is what is going to come in here, my mole to mole relationship. And once again, to cancel, so I have moles of nitrogen on the top here, which means I want it on the bottom here to cancel out. So in my balanced equation, I have 1 mole of nitrogen for every 3 moles of hydrogen. So that's going to cancel my number of moles of nitrogen. So at this point, I have done 2 calculations converting from mass of nitrogen to moles of nitrogen, and now from moles of nitrogen to moles of hydrogen. And then the last thing I need to do is to convert from moles of hydrogen to a mass of hydrogen. So here I'm going to need my molar mass for hydrogen, which is 2 atoms of hydrogen which have an atomic mass of 1.01, which is going to give me 2.02 grams per 1 mole. So here I want moles of hydrogen on the bottom. So for 1 mole of hydrogen, my mass is 2.02 grams. So that will cancel out my moles of hydrogen, and that means my units in the end are a mass in grams of hydrogen. So here, I don't have to calculate each step separately. So I don't have to calculate the number of moles of hydrogen, then the number of moles of hydrogen. Sorry, did I say hydrogen here? The number of moles of nitrogen, then the number of moles of hydrogen, and then the mass of hydrogen. So I can plug this all into the calculator and end up with a mass of hydrogen. So anything on the top is a multiplication, anything on the bottom is a division. Anything that is a multiplication or division by 1, we can ignore. So 18.6, we don't need the times 1, divide by 28.02, multiply by 3, multiply by 2.02. And that is going to give us 4.02 grams of hydrogen are needed for 18.6 grams of hydrogen. So this is once again where our mole to mole ratio does not give us any idea about the mass. So here in terms of moles, I need 3 times as many moles of hydrogen as I do nitrogen. But when I look at mass, my 1 to 3 ratio does not show up in any way, shape, or form when I look at the mass. So I have 18.6 grams of nitrogen for 4.02 grams of hydrogen. And that is because every atom of nitrogen has a mass of 14.01 14.01 units. So every mole of nitrogen atoms would be 14.01 grams, whereas every mole of hydrogen atoms is 1.01. So because it's a much smaller atom, it has a much lower mass, the mole to mole ratio in my equation doesn't actually give me an idea as what I actually measure is masses. So this is why we have to do a conversion from a mass we start with to a number of moles, use our balanced equation for that mole to mole ratio, and then convert to mass again. So another example with the Haber process, how many grams of ammonia are produced if there are 28.9 grams of hydrogen and an abundance of nitrogen? So that just means that all of the hydrogen will be able to react because I have more than enough nitrogen. So my starting point, 28.9 grams of hydrogen. We just saw in the previous example that the molar mass of hydrogen is 2.02 grams of hydrogen for every mole of hydrogen. So grams goes on the bottom to be able to cancel. Then I want to use my mole to mole relationship between hydrogen and ammonia in the balanced equation. So in the balanced equation, I have 3 moles of hydrogen. So that's going in the denominator to be able to cancel with the moles of hydrogen in the numerator there, and 2 moles of ammonia are produced. So now I need my molar mass for ammonia, which is 14.01 for nitrogen plus 3 times 1.01 for the 3 hydrogen atoms, which is going to give me 17.04 grams per mole. So 1 mole of ammonia, so moles ammonia on the bottom to cancel. 1 mole of ammonia has a mass of 17.04 grams. So my final units then are a mass in grams of ammonia. When I plug in 28.9 divided by 2.02 times 2 divided by 3 times 17.04, that is going to give me 162.53 grams of ammonia. And if we are looking at significant digits, I'm given 3 significant digits in the one piece of information I'm given. So my final answer would be 3 significant digits as well. We haven't talked about this a lot, but for those of you taking physics or who have seen this, feel free to use this to practice your sig digs and scientific notation. Next example, so rocket fuel, back to that. So how many grams of hydrazine do I need to produce 250 grams of water? So my starting point, 250.6 grams of water. I want to convert that to moles of water using my molar mass. So my molar mass is 2 hydrogens plus 1 oxygen, which is 18.02 grams per mole. So my grams go on the bottom to cancel out, 18.02 grams of water per 1 mole of water. Then I'm going to use my mole to mole ratio between water, so 4 moles of water in my balanced equation for every 2 moles of hydrazine. Now here you have a 2 to 4, which you could write a 1 to 2 ratio if you like. If you just want to use whatever numbers are in the balanced equation, you can do that as well. So that would leave me in moles of hydrazine, and now I want to convert to grams of hydrazine. So my molar mass for that is 2 atoms of nitrogen plus 4 atoms of hydrogen, which is going to give me 32.06 grams per mole of hydrazine. So 1 mole of hydrazine has a mass of 32.06 grams. So that is now going to leave me in a mass of hydrazine. So 250.6 divided by 18.02 times 2 divided by 4 times 32.06. And that's going to give me 222.9 grams of hydrazine. And I had 4 sig digs here, so 4 sig digs here. And if you haven't covered significant digits in another course yet, don't worry about this for now. Okay, so it's incredibly important to make sure that the equation is balanced, because the balanced equation is what gives us the correct mole to mole ratio. So if the balancing is not correct, or if it's not balanced, that is going to skew all of the calculations we do. So that's incredibly important to make sure that you have a balanced equation. The stoich only applies when we're talking about moles. So if I have a 1-to-3 relationship between nitrogen and hydrogen, that only applies in terms of a number of moles, not the mass. So we saw that 1-to-3 ratio in terms of moles, still in terms of mass, was less for the 3 moles of hydrogen compared to 1 mole of nitrogen, because the masses are based on which atoms something is made of and how many atoms. So based on the molar mass, which is different for every single element and compound. So because of that, we can't relate masses to masses, only moles to moles. And this one relevant if you've covered sig digs elsewhere. Wait until you get to the final answer for sig dig. So as you do each calculation, you want to keep as many decimal places as possible. So that's really going to be more relevant to the example that I redo in the separate stages next. If you are using the unit canceling method where you do all of your calculations in one go, then you get to the final answer in one step anyways. So that's not applicable there. So if you're fine with that unit canceling method, then you can end here. And if you aren't quite sure, or if you want to see the separate equations, then you can follow along. So the first example we did, how many grams of hydrogen are needed for 18.6 grams of nitrogen? So our flow chart that we looked at said that we need to convert this to a number of moles first. So the first step would be for nitrogen. We know we want to know the number of moles we have, and we know that our mass is 18.6 grams. So what we want is to solve for the molar mass so that we can connect our mass to a number of moles. So for nitrogen, our molar mass is 2 times 14.01 for the 2 nitrogen, which is 28.02 grams per mole. So my number of moles is equal to mass divided by molar mass. So 18.6 grams per 28.02 grams per mole. And that is going to give me 0.6638 moles. So this is where the sig digs comes into place of you can even go further than 4 decimal places here. So the more decimal places you have, the more accurate your final answer is going to be, and then you can wait until the end to do your rounding. So the other thing you can do if you like this method of going one step at a time is leave your answer up in your calculator and do the next calculation with that full answer there. So even though I'm only writing down 4 of the decimal places on here, my calculation I can do with all of the decimal places that the calculator shows me. So I know that 18.6 grams of nitrogen is 0.6638 moles of nitrogen. So now I want to figure out, based on my mole to mole ratio, how many moles of hydrogen would be needed. So my second step, is to use my mole to mole ratio. So I have in my balanced equation 3 moles of hydrogen for every 1 mole of nitrogen. and I want to figure out how many moles of hydrogen 0.6638 moles of nitrogen are. So to solve for x, I'm going to undo that division by 0.6638 by multiplying it over to that side. So keeping in that number in your calculator, the 0.663 and whatever the rest of the digits there are, I'm going to multiply that by 3, divide by 1, which I don't have to actually plug anything there. And so that would give me the number of moles of hydrogen is 1.9914. So now that I know my moles of nitrogen, my last step, of hydrogen, my last step is going to be to calculate the mass. So my number of moles is 1.9914. And then I need my molar mass. So my molar mass is 2 atoms of hydrogen. So 2.02 grams per mole. And to solve for my mass is equal to number of moles times molar mass. So I have 1.9914 moles times 2.02 grams per mole. So my moles will cancel. And once again, if I keep in the number in my calculator, so not rounded to the 4 decimal places, but the full number, multiply by 2.02, and I'll end up with 4.02 grams of hydrogen gas are needed for 18.6 grams of nitrogen. So this does the step-by-step, converting the mass you have into a number of moles for that substance. Then in step 2, using your mole-to-mole ratio from your balanced equation to solve for your number of moles of the other substance that you are looking for, and then converting that number of moles for the second substance into a mass using its molar mass. So when you use this ratio here to set up this equation, it is important that if I have hydrogen on the top and nitrogen on the bottom over here, that I have hydrogen on the top, nitrogen on the bottom over here. And these two come from my balanced equation. These two come from the actual amounts I have. So I need to make sure that I have my fractions set up in the same way.